Initially, there was an infinitely dense mass of matter. This mass underwent an explosion that gave rise to the formation of atoms, molecules, stars, and galaxies that we can observe today. For decades, this has been the explanation offered by physicists. However, recent research has introduced a new perspective that suggests the universe does not have as early an origin as initially believed. Instead, it may be part of a cyclical process in which the universe goes through a series of cycles of expansion and contraction, possibly in an infinite loop. Brian Cox, a renowned physicist, has also raised doubts about the Big Bang theory, arguing that something cannot arise out of nothing. This questioning adds an intriguing element to the discussion. In addition, research from the James Webb Telescope has revealed information that contradicts the idea that the Big Bang marked the absolute beginning of the universe. This leads to the fundamental question: if the Big Bang was not the beginning of the cosmos, then what was? Join us on this journey to the beginnings of the cosmos, where we will explore the frontiers of the Big Bang and answer this question and many more. If you are interested in keeping up to date with news about the universe and its surroundings, subscribe to our channel, hit the like button, share this video to reach more people, and turn on the notification bell. Scientists have developed a detailed understanding of the universe in its earliest stages, known as the Big Bang theory. According to this model, the universe was much smaller, hotter, and denser than it is today. Approximately 13.8 billion years ago, during that period, all the elements that make up our world were formed in a matter of minutes. In this theory, our universe, including stars and galaxies, was once as tiny as a peach and had an extremely high temperature of over a quadrillion degrees. Interestingly, this astonishing narrative aligns consistently with all current observations. Astronomers have investigated everything from the remnant electromagnetic radiation of the early universe to the abundance of the lightest elements and have found that everything agrees with the predictions of the Big Bang to the best of our knowledge. This description fits the reality of our universe perfectly. However, despite its apparent robustness, we know that the Big Bang theory is not the complete picture. There's a missing piece to this puzzle, and that piece is an understanding of the first moments of the universe. This challenge is due in large part to the limitations of the physical theories we currently employ. The combination of general relativity and high-energy particle physics provides us with a valuable conceptual framework. However, as we delve deeper into the initial moments of the cosmos, the mathematical complexity increases significantly, reaching a point at which our current methods cannot provide meaningful solutions. One indication of this difficulty is the existence of a singularity, a point of infinite density at the beginning of the Big Bang. This notion suggests literally that the universe was once compressed into an infinitely small and dense state, which seems to be absurd. To address this challenge, we need to explore new frontiers in physics, develop an approach that overcomes these limitations, and provides a more complete understanding of the first instance of the universe. Our current instruments and theoretical frameworks are not robust enough to address this challenge. So we need to develop new physics that can encompass and explain gravity and the other fundamental forces at extreme high energies. This is precisely where string theory comes into the picture. This theory aspires to be a physical model capable of unifying gravity with the other fundamental forces, especially at ultra-high energies. In essence, string theory posits that it can provide an explanation for the first moments of the universe. Within string theory arises the concept of an aeon, which takes its name from the Greek word meaning configuration or age. This idea suggests that the Big Bang, as we know it, was the result of an earlier event, implying that it was not the absolute beginning but rather a part of an ongoing process. Extending the notion of an aeonic universe has led to the development of a related theory called cyclic cosmology. Although the idea of a cyclic universe has been considered for millennia, string theory provides a solid mathematical basis for this conception. In the framework of cyclic cosmology, the universe functions as if it perpetually oscillates between large explosions and collapses in an endless cycle that extends infinitely into the past and future. This theory of cyclic cosmology was proposed by the eminent physicist Roger Penrose, who was awarded the Nobel Prize. Penrose was intrigued by a remarkable mathematical relationship between the early universe, characterized by extreme density, heat, and smallness during the Big Bang, and the future state of the universe, which is characterized as extremely cold, expanded, and devoid of matter. The theory suggests that these two states become mathematically identical when pushed to extreme limits. Although it may seem paradoxical, the total absence of matter could be the driving force behind the creation of all the matter we observe in the universe. From this perspective, the Big Bang originates from what remains almost imperceptibly after all the matter in the universe has been consumed by black holes that eventually evaporate into scattered photons in a vast void. The universe emerges from what, from another point of view, essentially approaches nothingness. Although this nothingness is still a form of something that constitutes a physical universe, albeit an empty one, the mystery lies in how the same state can be interpreted as both a cold, empty universe and a dense universe depending on the point of view. The key to this understanding lies in a complex mathematical technique called the conformal transformation, which is a geometric transformation that changes the size of an object while retaining its shape. Roger Penrose showed that the cold, empty state and the hot, dense state can be connected through the scale transformation, aligning their spatiotemporal structures despite their differences in size. However, Penrose argues that the concept of time loses its relevance under these extreme physical conditions. In cyclic cosmology, the sequence of events unfolds from an old cold state to a young hot state. The presence of the hot and dense state is the result of the previous cold and empty state. However, this causal relationship does not follow the usual pattern in terms of time, since in these extreme states both size and time lose their conventional meanings. The cold empty state and the hot dense state exist on separate timelines, which means that from the perspective of an observer within its own time frame, the cold empty state would continue indefinitely. Physics and philosophy are intertwined in this realm of cyclic cosmology. It provides speculative and detailed explanations for the origin of these cycles. However, even if Penrose's ideas gain support in cosmological advances, a deeper philosophical question still lingers about the origin of physical reality itself. How did these cycles come into existence? This leads us to ponder the reason for the existence of something rather than nothing, which is one of the fundamental metaphysical questions. For our purposes of discussion, we will focus on explanations within the realm of physics, and there are three possibilities to consider in exploring the origins of these cycles. First, there may be no physical explanation at all. Second, there could be an infinite series of cycles where each cycle represents a different universe and the initial quantum state of each universe is somehow determined by some aspect of the universe that preceded it. Finally, there is the option of a single cycle in a repeating universe where the beginning of the cycle is explained by some feature of its own end. These possibilities are attractive because they avoid the need for uncaused events and provide a more complex explanation within the physical framework. In the realm of physics, Penrose proposes the idea of an endless sequence of cycles influenced by his interpretation of quantum mechanics. In quantum mechanics, a physical system exists in multiple states simultaneously until it is observed, at which point it randomly collapses into a single state. Penrose suggests that each cycle is influenced by random quantum events that give rise to variations between cycles. This concept opens up promising possibilities for experimental physicists, as it suggests the possibility of detecting subtle traces or anomalies in the remnant radiation of the Big Bang. The quest to understand the origins and nature of the universe has been a fundamental pursuit of human curiosity and scientific inquiry for centuries. From ancient philosophical speculations to modern cosmological theories, humanity has continually sought to unravel the mysteries of existence itself. In the context of contemporary astrophysics and cosmology, the exploration of cosmic origins has led to profound discoveries and intriguing theoretical frameworks that challenge our fundamental understanding of time, space, and matter. One of the enduring questions that have captivated physicists and cosmologists alike is the nature of the universe before the Big Bang. While the Big Bang theory has provided a compelling explanation for the evolution of the universe from a hot, dense state to its current expansive form, it leaves open the question of what preceded this cosmic event, if anything. The concept of a pre-Big Bang era raises profound philosophical and scientific implications, pushing the boundaries of our knowledge and understanding. Several theoretical paradigms have been proposed to address this question, each offering unique insights and perspectives on the early universe. One such concept is that of the multiverse, which posits the existence of a vast ensemble of universes, each with its own distinct physical properties and fundamental constants. In the multiverse framework, our universe is just one among many, each emerging from different initial conditions and governed by its own set of physical laws. The idea of a multiverse arises naturally from certain interpretations of quantum mechanics and cosmological inflation theory. According to inflationary cosmology, the rapid exponential expansion of spacetime in the early universe could have led to the formation of pocket universes within a larger multiversal landscape. Each pocket universe would have its own unique properties, shaped by random quantum fluctuations during the inflationary epoch. While the multiverse hypothesis remains speculative and difficult to test empirically, it offers a compelling solution to the fine-tuning problem in cosmology, the apparent improbability that the fundamental constants of nature are finely tuned to allow for the existence of complex structures such as galaxies, stars, and life itself. Another intriguing concept that challenges traditional notions of cosmic beginnings is that of eternal inflation, proposed within the framework of inflationary cosmology. Eternal inflation suggests that the universe undergoes an endless cycle of inflationary phases, each giving rise to new regions of spacetime with potentially different physical laws. In this scenario, our observable universe is just one of countless regions within a perpetually expanding cosmic foam. The idea of eternal inflation raises profound questions about the nature of time and causality in the multiverse. If inflationary bubbles spawn new universes indefinitely, then the concept of a singular origin or ultimate beginning becomes increasingly elusive. Instead, the universe appears as a dynamic and ever-evolving entity embedded within a larger cosmic fabric of inflationary growth. In recent years, advancements in theoretical physics have also spurred interest in alternative cosmological models that challenge the conventional narrative of cosmic origins. For example, some researchers have explored the possibility of a cyclic universe where the Big Bang is not a singular event but rather one phase in an endless cycle of cosmic expansion and contraction. According to cyclic cosmology, the universe undergoes successive cycles of creation, evolution, and destruction, each culminating in a cosmic collapse followed by a new Big Bang. The cyclic universe hypothesis draws inspiration from ancient cosmological ideas and modern theoretical frameworks such as string theory. Within the framework of string theory, which posits that fundamental particles are not point-like objects but rather tiny vibrating strings of energy, the concept of a cyclic universe emerges naturally from certain configurations of the theory. String theory suggests that the universe may exist in a higher dimensional spacetime where cycles of expansion and contraction are a natural consequence of the interplay between fundamental forces. While the cyclic universe hypothesis remains speculative and faces significant challenges in terms of observational evidence and theoretical consistency, it represents a bold attempt to reconcile quantum mechanics with general relativity on cosmological scales. By proposing a continuous cycle of cosmic renewal, cyclic cosmology offers a tantalizing possibility of a universe without a definitive beginning or end, where each cycle builds upon the remnants of its predecessor. In addition to theoretical frameworks, observational cosmology has also provided crucial insights into the early universe and its evolution over cosmic time. The discovery of the cosmic microwave background, CMB, radiation in the mid-20th century provided compelling evidence for the Big Bang theory, offering a snapshot of the universe when it was just 380,000 years old. The detailed measurements of the CMB by satellites such as the Planck Observatory have enabled scientists to map variations in temperature and density across the early universe with unprecedented precision. Moreover, observational cosmology has shed light on the large-scale structure of the universe, revealing the intricate web of galaxies, clusters, and cosmic filaments that span billions of light-years. By studying the distribution of galaxies and measuring their redshifts, astronomers have been able to trace the expansion history of the universe and infer its age, composition, and fate. One of the most remarkable discoveries in observational cosmology is the existence of dark energy, a mysterious form of energy that pervades the cosmos and is driving its accelerated expansion. First inferred from supernova observations in the late 1990s, dark energy constitutes approximately 68% of the total energy density of the universe, making it the dominant component of the cosmic energy budget. The presence of dark energy poses a profound challenge to our current understanding of fundamental physics, as its origin and nature remain poorly understood. Some theories suggest that dark energy may be a manifestation of the vacuum energy predicted by quantum field theory, while others propose modifications to Einstein's theory of general relativity to account for the observed acceleration of the universe. In parallel with observational efforts, experimental physicists are actively searching for new particles and interactions that could provide clues to the fundamental nature of dark energy and other cosmic mysteries. Projects such as the Large Hadron Collider, LHC, aim to probe the frontier of particle physics by colliding protons at unprecedented energies, potentially revealing new physics beyond the standard model. Furthermore, advancements in astrophysical instrumentation have enabled scientists to explore the universe across multiple wavelengths of the electromagnetic spectrum, from radio waves to gamma rays. Observatories such as the Atacama Large Millimeter/Submillimeter Array, ALMA, and the Hubble Space Telescope have revolutionized our understanding of star formation, galaxy evolution, and the cosmic distribution of dark matter. Looking ahead, the next generation of observatories, such as the James Webb Space Telescope, JWST, and the Square Kilometer Array, SKA, promises to unlock new insights into the early universe and its fundamental constituents. These cutting-edge instruments will enable scientists to study the first galaxies, probe the epoch of reionization, and search for signatures of primordial gravitational waves left over from the Big Bang. In conclusion, the quest to understand the origins of the universe represents one of the greatest intellectual challenges of our time. From ancient myths and philosophical inquiries to modern scientific theories and observational discoveries, humanity's exploration of cosmic origins has yielded profound insights into the nature of reality itself. As we continue to push the boundaries of knowledge and exploration, new theoretical frameworks, observational techniques, and experimental technologies will undoubtedly shed light on the fundamental mysteries of existence and our place in the cosmos.